morning. Welcome to the data science program conducted by IIT Guwahati. In the previous sessions, we were looking at the module called computer vision, and in that we were mainly concentrating on the deep learning fundamentals starting from the convolutional neural network. And specifically in the previous class, we were looking at the improvements in CNN compared to the other neural network or simple neural networks, artificial neural networks with a large number of hidden layers. Compared to that, what are the improvements we have? Few of them we have considered in the previous class. So let's quickly go through that and then we'll resume from where we left. So the first problem which has been addressed is called as a vanishing gradient. When we have huge number of hidden layers between the input and the output layer, we observe that the error back propagation is not going to happen efficiently as expected. This is because of the gradient or the change in the error is not able to reach to the towards the input. Many layers which are close to the input layer, many hidden layers close to the input layer, they are not going to get this error. So mainly because of the derivative of the activation function, since we are using the sigmoid function, its derivative is very small. So derivative getting multiplied by other smaller numbers such as error, we will not be able to get the we see that, right, the value keeps on reducing and it becomes closer to zero as we have huge number of hidden layers. So that's the first thing. Then we looked at the second issue called as overfitting. So overfitting is characterized by the error increasing after a certain level of complexity. There is a best fit. Beyond that, if you further increase the complexity in terms of the number of hidden layers, we see that the error increases. Error initially decreases, optimum value then increases. So this problem is overfitting, right? We saw two different graphs corresponding, right? And in order to solve that, we use an approach that is considered as a dropout, right? So researchers uh, have worked on this particular concept and they have given a range like 0.25, 0.2 to 0.5, right? You can have a range, right, for different layers. Then we looked at the computational load, right? So how the efficient usage of GPUs, uh, TPUs, as well as the efficient algorithms, efficient approaches, right, in updating the weights when you have a huge number of hidden layers, right, is capable of bearing the computational load that is required. So then another concept, this is actually called as a regularization, right? It's not a problem, but it actually increases the weight updation. That we have considered what is called as a momentum earlier, right? So also we define what is called as a cost function. Two types of cost functions were also being introduced, right? So in addition to that, you can use a term called regularization term to our cost function, that is J, right? So here we can see that the first part of the J we already have considered as a part of the cost function. You can add another term, right? Observe that there is a constant lambda into half is a scalar, right? You can use it, you can neglect it, doesn't matter. So some of the authors will use there is a divided by 2. Otherwise, anyway, that doesn't make a large difference even if you omit that. Into magnitude of W squared. So as we have been using W for weights, so it's the same W, right? We are trying to use the sum of the weights into the cost function multiplied by a factor like lambda, right? So this is also going to help, right, in providing a much proper direction. So you can also get a better cost function if you use the values of weights to the cost function, right? Every weight, whatever weights you have, you try to maybe you can square it. Anyway, we know that weight will be smaller normally, right? It's a squared value multiply by square it, sorry, square, and you'll definitely take an sum of that. Okay, then multiply by a lambda smaller factor, keep between 0 to 1, and right, you can use that. That's the first term. All right, same thing even for the cross entropy, right? So this is that method. You can add that same term as a regularization. So let me define two types of regularization here itself, right? First thing is that you take a square, right? Otherwise, we can also see there is another method which keeps only the w, only the magnitude of w, right? So magnitude of w can be used, or the square can also be used. So the first term, you simply take a magnitude, is considered as L1 regularization. We are going to see that many times, right? At a later stage when we write the codes, right? Some of the codes we may use regularization. Some codes we may not use regularization. Okay, it's an optional case because we know that, right? Without this cost function also we can write code. Like simply calculate error and use the error as the cost function. Okay, so the basic idea is that we have a lot of options. We can try which one suits for our particular problem better, and you can use it, right? So regularization basically has fundamental two types. One is called as L1 regularization. I simply use a magnitude in this. In any of either you use the first type of J or the second equation, doesn't matter, right? You can use either only the magnitude W or magnitude square W. If you use a magnitude square, it is called as L2 regularization. So the name given is L1 and L2 for that. All right. So that's the additional part which the deep learning related or the deep neural networks take care while using the convolutional neural network or its different versions. Whenever we are trying to say we are trying to build the networks. All right. So because of this part normally we don't consider in the ANN weight updation. So because of all these factors, uh, we can observe better performance while we use the convolutional neural networks or any deep neural networks for when we try to implement that for a particular problem. All right. So I hope that is clear. Let's move ahead. All right. So we'll start with a quiz. Right? So the question that I have here is, so this is an approach. I want you to solve. All right. So take a paper and pen and try to solve this. So I want you to design a 2 into 2 filter. I don't know how many we require. So I have another question slash filters if required. Right? In order to detect a letter X written in a 3 cross 3 binary image. So let me make the points clear here. What you are supposed to do. Let me assume that we have an image. So they have mentioned that image is of size 3 cross 3. So they are writing a X over there. You want to detect the X wherever, right? We have one, right? Sorry, it's just all right. So let me erase what I just wrote. So this is just one. Okay. So all right, so I have one here. So this is a X, right? So wherever you see one that connect, right, it means make it some color so that you can see a X over there. So all the other values will be considered as 0 or -1 if you prefer, right? So let's keep it simple. Right? So this is what is the given image. On this particular image, let me say I want to detect this X over there. So I need a filter. So let me say so the question says that you need to design a filter. So what are the values inside this filter? 2 cross 2. What if you are writing it as a matrix? So what are the values of the 2 cross 2 matrix or matrices? Right? So that you can bring this over here, perform the convolution. So I start from this position, use a stride of 1, shift 1 by 1 position, and at the end. So So how many positions you have? Don't consider the padding, etc. Let's keep it as simple as possible. Right? We are trying to use that. So the result I'm expecting is definitely, so I'll change the color for say the result. So that, all right. So let me say I have a result over here. So the size of the result should be, right, how many positions I move. So first I keep as it is. So I'm going to get one location. Shift it to the right, one more position. So two columns, I understand. Then this will move down. Stride is one position down. So I'm going to get a, okay. So this is the answer. So from this, I should be able to tell that, yes, there is X in this page. Okay. So activation function will come into picture. That's going to come afterwards. But anyway, so, right. This is my target. So don't worry about the activation function, right? So at least try, uh, give me a matrix. Okay, so if you have an answer, you can tell the answer orally, or you can even type over there in the chat. Okay, so just enter the four values you get for a matrix, right? So this is my question. So whatever you see here is my question, right? What are the four values that are required to identify X in this particular image, right? That's a binary image. So I have a X already written over there. I just want to detect somehow. So use your own approach, because there is no standard procedure over here. We have never discussed anything standard like this. So there is no procedure like that. So in your own way, try to identify, right? How do you go ahead and how do you try to find out a filter so that you can detect the particular pattern I'm looking for. We are going to have two questions here. So the first question is this. Once you understand how to solve this, definitely you will be able to solve the second one. Okay. So try. Let's say we'll have 1 minute for that. It's pretty simple, right? Just perform a convolution. Take something very simple. Don't go for numbers like 2, 4, 6, 8. No, that's not required. Something very simple. So look at the pattern. I need a something diagonal, right? That's my clue. All right. So I have to detect ones in diagonal. All right. So use that as a logic, right? So which actually gives you an idea that do you need single filter or you need multiple filters, right? So that's the clue I can give.
Sir,
Yes,
so
yes, please.
yes, we need to tell the elements of this filter. What are
Yes,
the values in this? So I think
yes.
it's 1, 1, 1, 1.
1, 1, 1, 1. Okay. Fine. Let's see. Okay.
Mhm. Okay.
Keep trying
Uh,
others also, maybe. Okay.
okay. Yeah.
Because
Uh,
all ones, actually, it is not suggested, but maybe it will give you an answer. So
okay.
I'm not
Yeah.
very
For
sure that's
this
going to
one
give you an
zero
answer.
one for this X pattern, I think it will go 1, 1, 1, 1.
Okay. Okay.
Okay.
Yeah. Let's see. Let's see. Okay. So try others also, right? Anyway,
Okay. Yes.
you
Yes.
have an answer
Mm.
with you. Let's see. Okay.
Okay. Mm.
All okay, maybe last 30 seconds for others also to think about this, right? So the hint is this X either in terms of the main diagonal or the right other diagonal. I want to detect that, right? So let's look at the answer, all right? So let me first erase what I have Okay, so let's go to the answer. All right, so you see here, all right, so the its answer uses +1 -1, doesn't matter, you can even use 0. All right, so let's say we have two filters, right? One to detect the main diagonal, one to detect the other diagonal, right? So you see, this is the, okay, let me change the color. All right, so this is the first one, wherein you can see that I'm trying to detect this diagonal, right? So the product will be like this, +4, right? Are you getting that? Because I'm using +1 -1, so I'm going to get that. So this pattern is matching over here, right? So when you place it here, it matches. So you get answer +4, right? That does not match to the second position, so you get -4, right? And so on. Same thing will be repeated, -4 +4. So you see, if you activate using a ReLU, I'm going to get this in the sense, right? Along this, I have something like this. That's what is an indication, right? Anyway, I need to club this later. So somehow after this convolution, I am going for some other layer which actually clubs this. But the hint is that, okay, I'm able to detect this part. Same thing, right? Move to the second filter where I'm trying to detect the other diagonal. Like this. I place 1 over there, 0 on the other side. If you are dealing with ones and zeros, replace every -1 by 0. That's also going to give you the similar answer. 2 will be there, right? Okay. Right. So you see that here this is positive in the sense activate using the ReLU. This is the case, which indicates that I have 4, 4, saying that maximum highest values are saying that yes, I am able to find that. So need to club both the results to get an X over there. Okay, so that's one of the approach. Again, I'm not saying that this is the only approach, right? You can, right, think in your own way, and yes, we have several possible answers. Okay, I hope that is clear. So this is what was expected. Maybe if for those who say that question was not clear, right? This is what you're supposed to do. So as an exercise, let's go ahead. All right. So I want you to try this part. Okay. So design a 2x2 filter or filters to detect the. Okay, sorry, this is not X. My mistake. I'll just correct. It's detect O. Right. So the question is detect O in a 3x3 image. All right. So take your own time, maybe 1 or 2 minutes, so that now you know what you are supposed to do. All right. So detect a O in a 3x3. So how do you write a O? Maybe you have a question about that. I'll try to answer that. So the O can be considered in a 3x3. This is what, let's say, we are expecting, right? So O may not be able to write properly, let's say. So the O which I'm expecting is this, only these four. Again, I'm trying to make things simple for you. So maybe all the outer, right, position cells can be filled with 1, 1, 1, 1, 1. That's also an O. Okay, but I want to keep the problem simple. I don't want to go to that level. All right. So think about that, right? How to detect this, what filters you can use, question. Okay, right.
Sir, I have one question.
Yes, sure, please go ahead.
Yes, actually, just joined the class. So, in the previous this letter detection X, so why the feature map value is +4 -4?
It's
You can explain.
a result of convolution, right? So convolution, point by point you multiply, correct? So you see here, this is how you multiply. So in the first position, you get a 4 here just because this is the multiplication. 1 into 1 is 1. -1 into -1 is also +1. So 1 plus 1 is 2. -1 into -1 is +1. So answer is 3. Plus this 1 into 1. So 4.
Okay, sir. Okay, good.
Okay, it's a convolution. Simple convolution we have.
Okay.
Hello,
Yes, Sneh, please go
sir.
ahead.
I joined late, so can you brief me a little bit?
Yeah, sure.
process?
So the previous quiz was about the detection of a letter X. All right. So you can see that the X is denoted. I'll clear my drawing. Okay. So this is the X. Okay. So what you see here is the X. I want to detect that. I want to say that whether that is present in the given input 3 cross 3 matrix or not. All right. So what are the filters? The question was to find out these two, right? Whether 2, 3, you can use any number. So we are getting the answer quickly here with only two filters. So what are these filters was my question. Like in the current question, you can see that find out the 2 cross 2 filter so that I can detect a O in that image, O in the given matrix. That's my question. So anyway, people are trying to answer that question now. So the answers, as you can see here, these are the two answers. One is this filter, one is this filter. So how it's going to generate the required answer, we have solved the problem by doing the convolution. So perform the convolution of first filter with the given image or given matrix to get the feature map. So recall the convolution process we studied at the beginning of this whole this particular module.
Yes, sir.
So once you convolve, you get a feature map, right? So convolution resulted in that. Activate. So previous class we understood that okay, we are not going to use sigmoid, we will be using the Rayleigh. Negative terms will be eliminated. You put zeros in position of negative numbers, keep the positive numbers as it is. So wherever
Okay.
you have the highest values, it says that yes, whatever pattern you are trying to look at. So this is the pattern. Look at the filter one. It says wherever you have 1, 1, that's what I'm trying to detect. It says that yes, I'm detecting it in the image because I have a this particular pattern, right?
Okay.
So this is what I've detected. I'm detecting. Similarly, the second filter, after the convolution, I obtain the feature map, which says I detect the other direction. So that's what is this after the ray. So I am able to detect this part. So clubbing both of them, you are going to get the pattern. Yes, this says the whole idea is that yes, I am detecting a particular pattern in the given image.
Okay, sir.
So apply the similar logic and find out the other two filters, one or two filters. Again, I'm expecting two filters. I'll tell you what I'm expecting, right? So that I can detect a zero in the same 3 cross 3 image. Okay, so that's the question.
Okay. Okay, sir. Thank you.
Okay, so anyway, I think we had enough time here. So let's go to the answer. All right, so let me run this and see. Okay, so this is the expected answer. Again, you may go for a bigger level map or something. You may have different approaches as well. So this is not the only approach. One of the answers. So you see the O is detected in this fashion. Let's see. Okay, so assume that we are not moving to the other thing, wherever we have written -1. So that's what is a 0. So now filter 1 and filter 2. Okay, so this is going to generate this part saying that yes, I am detecting here. The 4 says that yes, the pattern which is this, right? This pattern is detected over here now and here now. So, right, that's what is the meaning. In the given image, I'm able to detect that over here and here. So I get these two, this and this. Similarly, you see the filters are pretty much similar. Same filters can be applied. So that's why, anyway, I'll come to that point later. So let's see. So we have a 4 here. We have a 4 here, indicating that that pattern has been recognized here. Because your pattern is this, right? See, the pattern is this. Wherever 4 is detected, that pattern is there. Again, a 4 is detected, that pattern is there. So that means I am detecting the other two. So when you club all of them together, you get this which says that yes, whatever pattern you are looking for, it is present over there. So what do we learn from these two? It's like, right, we can use, you see the filters are same, previous case as well as this case it's same, similar filters are used, correct? So that means we can use the similar filters inside our convolutional neural networks to detect various types of patterns. So you see that now whenever we design a CNN, we say that okay, I'll just fix that number of filters equal to 60, right? Maybe you may be able to recall the sequential networks we did the program, right, in initial phase. So where we used to say that okay, convolutional 2D layer of particular size, I say that okay, I need 3 cross 3 filters, I need 8 filters. So every problem I give, maybe it's the same thing which is processing your input data, right? Now it is we are trying to answer, maybe you had a question over there, how can we these 8 filters try to extract different features? Now you have an answer. You see, detection of X is also possible, 0 is also possible, right? Using similar. This is just a hint, right? Just to get an answer or that question which might be there in your mind at that time. So that time we didn't know what is convolution, how the things are happening. So I didn't try to answer at that point of time. Okay, I hope this is clear. Do you have any doubts related to what the two quiz questions we have? Okay.
Sir, if we
Yes.
give 1, 1, 1, 1, then directly we will get the O.
You
No?
get the O, right?
If we, yes.
Okay, possible. That's what I. So you have multiple solutions possible. Okay.
Okay.
Yes, absolutely. Correct. So let's move further. So the next topic, we are going in a little bit in depth today. So we are going to look at the theory as well as the programming aspect. Okay, so let's start with the CNN architecture. So this we already have seen. Fine. So I think we have a bigger number given. That's where I copied from. Okay, so let me go to the CNN architecture, right? So in the CNN architecture, basically the CNN architectures will follow a similar pattern. Like always, you have an input, it will go through a convolutional layer, followed by a pooling layer. Then you may decide that I want to add few more convolution, pooling, activation layer. This pattern will be repeated. So already we have seen some of the networks, right? Maybe at the initial phase, just to show you that how the practical convolutional neural networks are built, right? So if you remember that they were written in a vertical fashion, correct? So different types of different parameters were used in terms of the number of filters, the filter size, etc. Or the stride as well may be different, right? If you are able to recall, try to recall. We had a vertical stack of the various layers. So they were standard, right? Again, it's not that that's the only thing we can do. Definitely, we can make the modifications in them if required, or you can, if our problem is pretty much similar to the one which they try to solve, we can use, you can use as it is, no problem. Okay, so programming is what we have to do, that's all. So in the programming you can define a particular part, convolution followed by pooling followed by activation, define that as a function or as a class, right? And you can keep calling that again and again whenever required. That's the only thing from the programmer's point of view. So practical design says that okay, I use this layer, these many so this is the size of my filter, I use 8 filters, 16 filters, normally it's a 2 to the power. Okay, so followed by what activation function. So do you need a pooling? What is the size of the pool you use, and what is what type of pool you are going to use, average pooling, etc. Many poolings we have seen, max, mean, etc. Right. So this pattern can be repeated any number of times. So we also have understood the requirement of this repetition, because if your problem statement is in the sense, if there are many categories of images to be classified with complex representation of the features, right, then we might have to repeat these layers so that I can keep extracting more and more features from the images. I'm going to come to this part, how the features are extracted, and when I add a layer, what is that additional feature that we are going to extract, right? I'll demonstrate that when we move on to the object detection part. Okay, so that's the last part of this particular module. We may not be able to touch that today. Maybe the next Saturday's class will be on that, and we will try to finish the module. Okay, so that's the plan. So anyway, so idea is that as and when I add this particular layers repetition, convolution, pooling, plus activation maybe. So I repeat that means I'm trying to extract more features from that, right? So how we are expecting more features, what is that additional feature, we'll answer later. Okay, so this is repeated as we add more and more layers. Just understand that we are trying to extracting more features, right? Once this feature extraction is over by the convolutional neural network, on the last part you can see that we have the fully connected layer, right? So this is actually the linear, right? Normal neurons present over there, all are connected to each other. Each neuron is what? It's a linear classifier. So initially we had done this part also. We went in very detail just to make sure that you understand that each neuron is going to classify linearly. But when you club all of them, they are able to classify the non-linear problems as well. So we have the features coming, and the features are considered to be right non-linear, right? So in order to classify so many features which you have extracted before this by using the convolution pooling, right, that combination, we try to classify them using the fully connected layers. You can use multiple layers, you can use single layer, depends on the complexity. Now in the next section, followed by in the next slide maybe. So what we are going to discuss is that what are the various state of art networks that are present, right? So you will be able to see there, it's not that you use only one layer here. You may have to use multiple layers. People have done a lot of research on that, and then they are able to make a comment saying that we need 3 layers here, we need 4 layers. It's their research result, that's all. So whatever they have done, we are trying to show that, and we'll try to show the code corresponding to that. All right, we'll run a code on using that particular network, and we'll try to make a comparison as well. So many architectures are going to come now. So right, starting from the beginning, when the deep learning started, 1990s, right, mathematical work began, right? So that was also implemented, but there were they had no idea about the ReLU function or something. So they tried to implement using the sigmoid or something, but still the deep learning concepts began over there. We will be able to visualize that as well. Okay, so fundamentally, the neural network architecture will be like this. So you have an input, you have several repetitions of convolution, pouring, convolution. Some other additional parts also may come into this, but the big picture is this. So this is what is the stack of simply the signal flows from left to right. So we have stack of layers. So through that we will calculate. So once the ReLU was actually was invented and the usage was justified, right? So there onwards you don't have sigmoid coming into picture. You have all the layers with the array. Okay, so that's the general architecture what you are seeing on the screen, right? So let's move ahead and let's look at the modern architectures, right? So again, there are many architectures present. So in this particular part, we are going to look at the major ones which are considered as a significant improvement than the previous architecture, right? So also we are going to consider they were very famous at that time because they won some award, right, on a world level, international level competition, right? So such networks we are going to consider, right? So the first one is called as a LeNET. Some will call it as a LeNET as well, doesn't matter. So fundamentally we have two parts in this network. Okay, this was the first one around 1990, right? So it has two parts. there is a convolutional encoder. That's convolution. You can see here this part, right? Convolution pooling, convolution pooling. So you can see the exact size, right? Exact size and the shape, right? So this is 6028 into 28, right? It actually, sorry, it's not 6000, 6 into, okay, 28 into 28 repeated 6 times. All right, so there is a et over there. It's an original diagram taken from the research paper. All right, so the second says that 6 times 14 into 14, right? Then 16 layers of 10 into 10, then 16 layers of 5 into 5, right? So you can see that convolution, right? Feature map you get, right? So same thing, they have given different names for that. After that, at the end, you see we have a fully connected, it's, they named it as a dense. All right, so nowadays the dense means different. Okay, so anyway, that's, it's fine. So according to their terminology, we use it. They say that dense here they refer to every neuron in a layer is connected to every neuron in the next layer. That's how the dense layer was defined at that time, right? So that's a dense block consisting of 3 different layers with the fully connected, right, neurons. Okay, so this is what they had designed. Actually, this won a prize in an international competition. All right, so the features, right? So it's actually, we can see that, right, we have many convolutional layer, right, and sigmoid activation function. So it means, right, you understand that ReLU, max pooling, etc., right, they are going to work better, but I don't see them here because they had no idea, right? It was that, it was something like much before. So convolution layer uses a 5 cross 5, right? The kernel size, right, according to them, they have used this, right? Nowadays we can definitely modify this. If you want to change it to 3 cross 3, we feel 3 cross 3 is better, yes, we can do that. This is what the original work, right, carried out by the researchers. Sigmoid activation function. So we can see that the layers are spatially arranged inputs to a number of two-dimensional feature maps. Whatever input you give, it will be converted into a stack of feature map. You can see one behind other. Because I'm using so many filters, right? Each filter will generate so many feature maps. That's what. All right. So we know this. It's a result of a convolution, right? So each of the filter, right, what it is going to perform, they have mentioned that here. So first convolution layer has a 6 output channels because you have 6 different filters. Okay, each of size 28 into 28, right? There is a polling operation, right? So it is, you are moving with a stride 2, that also has been mentioned clearly here, right? So what happens, your size reduces. Okay, so that also has been mentioned here. So size bigger, when you do a polling, we already have seen that size reduces. So that's what is happening here. Then next layer, you have convolutional block, image and output with the shape given by. So we have a batch size, how many such filters you have according to the batch, the number of channels, right? Again, it depends on the number of filters you have, height and width of the image, right? It keeps on reducing. We can see initially maybe it is 28 into 28. As you propagate further, it reduces 14 into 14, 10 into 10, 5 into 5, and so on. So these are the way characteristics that you try to obtain. So what we do, in order to pass the output from a particular block to the dense block, right, there is a concept called as flattening, right? So flattening is very simple. So far we have not, though we have not discussed about that, it's pretty simple, right? So let us say I have, right, I have an image of, say, size 4 cross 4. All right, so when I say the image has a size 4 cross 4, so totally how many elements we have? 16 elements we have. If at all my next layer, right, so what's the size of the next layer here? Let's see that. So this is 120. So dense layer, the first one has 120. Right. So what we are supposed to do is that depending upon how many neurons you have in the next layer, convert your, say, again, I gave an example of 4 cross 4. So 4 cross 4 is 16, right? I am supposed to use 16 over there. So you convert a 4 cross 4 into a one-dimensional array. That's all. It's called as a flattening. You are trying to reshape your output so that they can be fed as input to the next layer. If at all they do not match, if at all the sizes of or the shapes of your matrices do not match output of one layer to the input of the next layer, if they do not match, then you need to convert this into the shape of your next layer. That process is what is termed as flattening. Okay, so here you see we must flatten. All right, so that's what is the meaning of flatten. So same concept they had used at that time. Okay, this concept was there, yes, because anyway everything is matrix multiplication. If that does not match, I don't have any other option rather than changing the size. All right, so that's what. Right. So you see here the features that represented in the form of matrix. Maybe it's a 4-dimension case. So batch size, number of channel, height, and width. So 4 values are there, right, corresponding to each of them. So you can think that it's a 4-dimension. So you see 4-dimensional input, transform it into a 2-dimensional case for a fully connected layer. Fully connected layers can be of 2 dimension, because whatever comes from the input is considered as a 4-dimensional data. All right, fine. So the sizes that have been used are this. Okay, so that's what have been used. So it's their research work, whatever they have found. They have written a paper, from that we got this. Now this is the actual structure they have used. This is the compressed word notation of the previous diagram what they have used. All right, so you see we start from the bottom and we move upwards. Okay, so the sizes, right, whatever the size you see here, 120, 84, 10, it's a fully connected layer present over there. Before that, whatever layers we had, they are present here. This is the input size, and the stride, whatever type of pooling you are using, whether it is a convolution layer, whether it's a pooling layer, etc., have been mentioned over there. Okay, so our idea is that we want to visualize this in the pattern. Also, we want to try to write a code whether this is going to work or not. So we are going to do that, right, before we proceed to the next standard or state of art network. All right, so what we do, we'll go to the Colab. All right, so I'll run the code in the Colab today, because it needs many of the tools to be brought in, to be imported, and I was facing some compatibility issue with the Python version we have and the tools we have. They're not matching. It was throwing some error on my PC when I try to run in the Jupyter. Okay, so anyway, so let me anyway, this gives you an idea how to connect the GPU, etc. I'll show you that as well. Okay, so what I do, I go for a reconnection, GPU at the back end. Let's see, let's connect without GPU, then we'll see. So what happens whenever you go through this? Normally first we go to this part and we'll say that we'll connect. Okay, so simply you connect, simply click on the connect, it will get connected. Once it gets connected, I can change my runtime. All right, so now it actually has got connected. We can see the resource. You see there is no there's no GPU connected. Okay, so let's try whether we get a GPU. So go to the runtime and change the runtime type. So yeah, you have the options like this. So none means it will allocate a CPU too. I would like to go with a GPU. Okay, and let me try to save this. And oh, it says that it cannot connect. All right, no problem. Let's see. Later on, we may get a chance to get connect. You cannot currently connect. All right, so normally we will be able to get connected. This is what I have seen earlier, because when I connected previously, it was a GPU. I'll show you that answer, because now anyway these answers are not valid because we connected once again. It's a new runtime, but I can show you that GPU. Yeah, you see here. So this result says that it's running on a CUDA, right? So it's actually an API by uh, the NVIDIA, which supports if you have a GPU in your system, or right now we are running on the Google's GPU, right? You are using the GPU to you are utilizing the GPU to run your code. Okay, so that happens. If now you see we don't have a GPU, so when I run this code again, right, you will see that we are not going to uh, get that CUDA on that. It will show that running on a CPU. Okay, so let me disconnect and connect once again, because if we get a GPU, we'll be able to run this code faster, right? So that's the overall idea here. So let me okay, restart. Let's see. Okay, it says it is initializing. It has been initialized. Let me change the runtime type. Let's say if we get, we'll do that. Connect without GPU. Fine. One last time I'll try. Okay. If still that is not going to work, yeah. Right. It says that it is GPU, but still, yeah. All right. That's fine. So now we need to import a particular library that is called as a D2L. It's a deep, yeah, it's deep drive library. All right, so that's actually it brings us the support required to run the deep learning based functions. Normally, it's not there even on the installation of Python what they have on their side. Okay, so we need to do this because next I'm going to call. Anyway, this is PyTorch, right? I'll do that. But whenever I say that, okay, bring me this, it will throw up an error saying that I don't have. Okay, even on the Python installation which is present on the Colab side. So we need to do this. Okay, so that's our first step. So anything which is not present in the Colab side, right, we can actually install it here. Like they're allocating a whole computer to you with certain amount of RAM, certain hard disk, right? If possible, you will get a GPU as well. But sometimes we get an error, or like we cannot allocate a GPU, then we should be able to find go with the CPU what they allocate. Okay, so you see many things are downloaded and installed on the particular system which has been allocated to you. All right, so then we'll go to this, right? Just run this, right? I'm able to import the various modules which I'm asking. Now let's go to the LeNET part which we are considering, right? Okay, so according to the requirement, right, you can see here we are, right, we are trying to design the network. So try to recall the structure, right? Anyway, don't worry, the diagram you may not be able to recall. Let me quickly show you this. We are trying to write a code to implement this, that's all. Okay, so right, you can see it's a NN sequential, right? And so first is convolutional 2D layer. From the bottom to the top, we are trying to write a code. Okay, so according to the size they have mentioned, right, we are writing the function. You see the sigmoid function you being used. So we just have to stick to the particular method or particular way of writing the code that we already have studied, right? We are simply trying to implement that over here. So if you are not able to recall how do we write this code, what is the syntax, you just have to go back. Anyway, I'm going to share you this code immediately after the class today, right? You'll be getting by the end of the day today. All right, so that you can compare whatever material we have shared earlier, the proper way of writing that, compare it with that, and you will be able to understand. So just understand here. So there is a convolutional 2D layer of a specific size, right? There is an average pooling according to the diagram, right? Convolutional 2D of various size, average pooling in 2 dimension, Then there is a flatten. Just now I mentioned that what do you mean by flatten. So here automatically it will identify what is the previous layer size, what is the next layer size, modify that data which comes from the output of the previous layer according to the next layer's size. It will automatically do, you don't have to do anything, but we need to remember the function. Okay, then the dense layers will come. So they can be defined by using the fully connection, right, between the every neuron present in a layer to the every other neuron that is present in the next layer. So how do you do that, right? You can simply call a linear. Now we understand that why we call that as a linear at the first place, right? So each neuron is a uh, linearly separable output, right? That produces a linearly separable. That learns something which it can identify in a linear space. Then all of them, when we club together, we get the non-linear case. That's why you see here, according to the size that is mentioned over there, right? So we have defined 3 different layers. Okay, so layers are defined. Pretty simple. This is the most simple architecture that we are going to see today, because this is the oldest one. They had no idea about, right, the advanced topics, right, because they were not at all implemented at that time. So the first part, right, simply let me run this. So it runs. Now I'm actually defining. So X is my input. So let's try to define some random inputs. All right, so it's random. I'm bringing the data set at a later, right? So for this, we already have defined the network over there. So I'm trying to, for a layer in the network, right? It's simple, the way of writing a program. For every layer that is present in the network, X equal to layer of X, pass this X through that and print out, right, what is there. So I'm just trying to print out what what is the size of the layer, what is the name of the layer, etc. using this. All right, you see it prints out, right? So convolution 2D layer, sigmoid, average pool, etc. Whatever we have defined in this particular part, right, we are able to visualize. So that's the use of this code. This is not required when I actually write a program to test something, to train and test something. This is just for a visualization purpose. All right, so we can neglect that as well. All right, moving ahead. So you see we are defining the batch size, right? So this is actually, the whole data set has 60,000 images. So you see that batch size, this is actually the mini batch. The concept which we are implementing here is a mini batch. So directly, so there is a MNIST data set which is present inside this D2L. That's one reason why we have used it, right? So as soon as I run this, we will be able to get that. Okay, that will come into the data set, will come into the memory of the Colab. All right, so that's why we are writing this. It actually calculates the training iterations and testing iterations, right? You see that the data gets downloaded, right? And I think yes, we ran that. Then now again, this is what we are writing here to calculate. Again, I was trying to run it on a GPU part, so this part of the code will take care of the implementation part on the GPU side. Okay, as of now, don't worry, because that makes things very complicated. If we try to analyze, don't worry, because mostly we are not running on a GPU as of now, right? So then this part is about the using the network, number of training iterations, number of testing iterations, the epochs, learning rate, and which device you want to run on, right? We are using them to do the, right, the testing part, sorry, the training part, and we will see that it's actually the function written. Now we'll call the function at a later stage. All right, so let me quickly run this part. We don't have to go through that. Now the actual training and the testing part comes in the picture. So I define the learning rate 0.9, number of epochs 10 times I want to go with this. All right, so we'll call the function. Okay, now you see it is actually, we don't have a GPU with us. Oh, sorry, some error. Let me see. It's still running. Let me see. Let me see. was expecting a graph here. Previously, we got a graph, right? So that's the graph. Actually, I wanted to show you how the that particular graph gets plotted when program runs. All right, so that was my uh, intention. But if we are not able to run this, then that means I don't have any option to show you that. Okay, so let me try once again. If it works, let's see. Otherwise,
So maybe like, okay, run even that GPU function, it may have a reference somewhere down.
yeah, I ran that. Okay, so you see here there is a tick mark saying that
Yeah, okay.
you ran that. Okay, I am running this as well as the next. I am doing that. All right. So but here we are getting some error. So only issue that we observed while using the Colab is that if there is a network issue or if there is some issue from their side, normally we are not able to come. Okay, maybe the previous time also when we were running, I faced a network issue from my side because of that runtime got disconnected, and later on I could never connect. So that was the issue, right? That's a common issue when we run on the Colab. Okay, so it's not running. Let me try to connect to a GPU once again. Maybe that will solve my issue. This is what I think. So let me change the runtime. So let me connect to none. All right. It says it is connected. Let me check. No, today morning when I was running, I could connect to the GPU. All right. So because of which it ran much faster. All right. Yeah. Now we are not able to due to the limits in Colab. I don't know. Normally, for one day, you will get an access to GPU. Right? So whenever we connect, that's what is happening. Okay. So let me try. Let me quickly try once again. Maybe I have already. It's a new. Let me try to run this. Cannot connect to. So that means it's going to run this very similar way. Okay, we will be getting the error. So I'm not going to run the remaining part of the code. What I wanted to do, I wanted to show that how it gets plot for every iteration. You will get the points getting added on your curve. Okay, but because of this issue, I will not be able to run other part of the code because if I run that, it gets erased and we will not be able to discuss over it. So for that reason, only this part of the code, when you get this document, please try to run by yourselves. Okay, and anyway, let's try one more time. I'll try to run each one. Okay, so
one like, okay, maybe a weird suggestion, just log off and log in to the like, okay, Colab again.
all right, let me check that. Maybe that will work. I'll try that. Okay, so let me save that before I log out.
And we are saying thinking the same code should run on our even local Jupyter notebook if everything is set up properly, right?
Yes, yes, yes. If you have, so the problem which I was facing was this: the D2L was not present in my system. I have the TensorFlow GPU, which is the TensorFlow is must. Okay, you can install the GPU or the other version. But when we install, you see that it actually says you can check here. So in order to install this D2L, we have many other things. So Panda should be of the same exact match because I have a different version. It says that it throws up an error saying that okay, your condition is not satisfied. When you try to install a particular version of Panda, it says some other, right? Some other version. This is not matched in your system. So you change that means something else will change. So that's a big problem when we try to install this on our system in a manual fashion. Okay, so that's a normal problem we face. Okay, when we try to install, so it still says the same. let me, okay, it's connecting, still connecting. Let's see, it's initializing. And okay, RAM has been allocated. One more time I'll try. Okay, previously the policy was you could use the GPU allocated to you for one full day. So that was the idea, but now I don't know, it might have been changed as well. All right, so maybe because of that. Okay, let me try a GPU if it works. I don't know, it says that use it only if you need. I don't know. Let's see. Yeah, no, it's not allocating. I think you can connect only once in a day. That's the new policy, I guess, because I already connected once and I tried, the code ran over there. Okay, so anyway, let's not waste the time. Let's proceed further. So let me run this part, because okay, anyway, we are not running the code. I will show the output we got earlier. All right, so only this part we have an error. I am supposed to get a graph that actually shows what is the loss for every iteration. I'll show the next graph, so that something like this. So this is what was expected: training loss, then the accuracy during the training, and the accuracy during the testing. So this three things, right, should be plotted as and when the iterations proceed. As and when we give the data set for training, this was being plotted. Again, in this case, whatever we see there, right, it's actually being plotted. All right, so for the next one that we are going to do later. All right, so that was the first the oldest state of art neural network, the deep neural network that was designed. Okay, right, let's move ahead. This is the second one, which is famous. Now you see, from 1990 we moved ahead to 2012. All right, so this is actually called as AlexNet, right, which actually won a award in 2012. So this particular network has 8 different layers. So what are the 8 different layers? You can see here. In input comes, again, this was a specific network designed to solve a specific problem. You see that the input is specified as a color image 3 cross 224 into 224. So square image with the color. So that's why you have a 3 into that. Okay, so that's the input. And the other feature of this particular network includes, we have first convolution layer, 11 into 11, 96 of those, and stride 4. Now you see the size of your neural network has been increased drastically. Previously we didn't have such big this thing, right? So you can see the next one, right? There is a pooling. Now you see a convolution, maximum pooling, convolution, right? Convolution, convolution. Yes, you can use, right? It's not necessary that you have to use it after convolution, you should go for pooling. No rule like that, right? So here they have used a stack of convolution followed by again convolution followed by another convolution. Yes, it's allowed. So we may have a question in the mind that yes, can I do that? Yes, right? So you can do that. What type of features you may get, right? Maybe it may vary from the layers that I'm going to use, right? So the size is also, you can see, right, compared to the previous one, the size of each of the layer or the number of filters that you are going to use has been increased drastically. You see 384, 384, 256, right? There is a padding that is happening with one. Now, since we have gone through the basics, at least we are able to understand what is the operation that is being carried out. So maybe there is a lot of research that has been carried before coming to this final stage, okay, final architecture. But anyway, we understand at least these words, right? So fully connected 4096, fully connected, and fully connected 1000. So that's the fundamental structure. So now, since we know one of the previous the standard architecture, let's try to compare. All right? So this is the comparison which we could identify between them. Maybe there are few more examples also, right? Maybe when you do a research on this by using some references, maybe you are able to identify more. Okay, right. So you see the number of layers more here. That's why, right? We can say that it's deeper. right? This particular neural network is more deeper compared to that. That's the first example we understand, right? So this AlexNet consists of total 8 layers because of that deepness what we discussed, 5 convolutional, 2 fully connected hidden layers, and 1 fully connected output layer. So the last layer which we see at the top is the output. Okay, so AlexNet used ReLU instead of Sigmoid because it's comparatively this is more recent. By this time, yes, ReLU was being used. Okay, so now I'll show you the code. This is the code for that. We have used 8 different layers overall. Okay, in addition to that, so there is a dropout which was not mentioned over there, just right. So this is the advanced, actually original version and the most recent version has some differences. Okay, so there is a dropout, right? Just understand that, right? There is a dropout being used. So you see there is a number 0.5, 0.5, right? So we mentioned the range in a particular layer. You can use up to this value, right? So 0.5 was there, so here it's being used as 0.5. Note that, right, the ReLU is being used, and also you see the padding values whichever mentioned over there we are trying to use. So this is pretty much similar. Okay, right. So everything else you can see the last one is 10. This is because our output has 10 different values coming up, because this whole problem is about classification of handwriting digits 0 to 9. So 10 classes. So just remember what we discussed in yesterday's session. So if you have a multi-class, I need so many neurons in the output. Okay, so that's about this. Then we are trying to visualize the network over here. Okay, and by printing out what layer it is and what is the size. All right, what's the size of each of them we are trying to do this. So then we define the batch size. So again, this is a variable, simply kept to 128, keep changing. You can change this and you see the effect. Okay, so when you run this, try to change this and run. All right? So then learning rate, right, the number of epochs, etc., right, you can define, you can vary these values as well, right? Then call the function train, and when you train that, right, you will be able to visualize what is the loss. This is the final value. Okay, every time it gets updated, final value what we get we can see. So the training accuracy we can find is 88%, and the testing accuracy came to be 87%. So this will definitely vary when you increase the number of epochs, when you change the learning rate, you will see the effect. So my intention was not to optimize this model, so I never went, simply I entered a value, I run it. Okay, so when you run this, you are getting this. So you can see that as expected, initially there is a high loss, but it keeps on reducing as you progress. Similarly, right, the accuracy keeps on increasing as the training progresses. All right, so training as well as testing, we can see that the accuracy increases. Right, so whatever we had expected, that is happening. And yeah, we are expecting something close to 85, 90 normally, right? So we are coming close to that. All right, so hope this is clear. Please try to run this by yourself, and right, if you have any doubt, you can come back to me once you run. All right, so after this, the next one, which is pretty much famous, even nowadays we are going to use, we will be using it. It's called as a VGGNet. Okay, it was invented by the Oxford University. There is actually a team which works on the visual geometry. It's called as a visual geometry group. So hence the name given here is VGGNet, right? So they have an idea. So they are considering, whenever they did the research, they consider that AlexNet or the previous other networks, right? You don't have a specific, you cannot use that as a template, so that you can use many copies of them to build your network. So it's something like they have something very standard. At their time, it worked very fine, fantastically, that because at that time when AlexNet came, it was something, a very huge achievement, right? So go to the internet and find out more about that. Okay, so you get a lot of details about that. So the problem associated this is it's not like a template. Anything which you have so far, right? It cannot be used as a template or a simple block. You don't have something like a block. That block can be repeated n number of times to get. So something like I know that I have a convolution layer, I have a pooling layer, but that is not standard block, right? They wanted to build a block like structure. That block should be used repeatedly if you want to improve the complexity or improve the number of hidden layers, etc. So that was their idea. So they applied that idea to build their network, right? And the first part of that is called as a VGG block, right? So they defined, okay, this is what is the fundamental block we are going to use. You can repeat this any number of times as required. So that was the fundamental thing. So you can see here, according to them, the VGG block has a convolution layer, right? Remember one thing. So we are under the particular model, which is computer vision. So we are trying to relate everything to the same problem. Every code we are running on the same problem. I want to classify that image data, right? So that's why. So again, in this particular discussion also, we are talking only about the images. That does not mean that you can give other inputs. Okay, so when you run, you have other inputs. Definitely try with that. Okay, so see, I talk about the resolution because of the same reason. We are discussing about the images, image classification using the computer vision techniques. All right. So again, you have these three, right? So there is a convolution layer, ReLU, followed by a pooling, right? So this has to be repeated. So let's see whether we have a block. Yeah. So again, this diagram is a comparison, right? So first one is the AlexNet. This is the AlexNet. Compare that with, so there is a VGG block. It's a predefined block. Now you see you can use that any number of times. So you see there is a dot 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 indicating that you can repeat this. In the sense, they did a research and they found that if you use this particular combination once, instead of using something else like this gives you a better extraction of the feature. That's what was published in their research paper as well. Okay, so that's why you can actually stack them again and again, right, to get a better the performance. So at the end, right, they say that yes, you use a fully connected layer of the particular size. Okay, so this is what was the architecture they developed. So its modified versions are still existing, still they are performing, right, in a very excellent manner to provide you a better accuracy, good results, right, time, etc. Okay. Yeah, just 1 second, Jyoti. I'll share you that. Okay, I can share the code. Correct. So I'll go to the share option. Anyone with the link? I'll share you the link. All right, in the chat box, so that people please try to run. Right. Yeah, that's a good suggestion. Thank you, Jyoti. Yeah. So everybody, please try to run on your system. Try to connect to GPU. Okay, so don't get connected to the CPU version. Connect to GPU. That will run faster. All right. So that was the VGGNet. So let's quickly go through the VGGNet. So now you see we are using a block. We first need to define what is called as a VGG block. So you can see that here we have a code, right? That code is talking about the VGG block itself. So first part should be the VGG block. So you can see that according to the specification, right, you may require the number of convolutions, how many input channels and how many output channels for that particular block. According to that, I have to define, right? So we are defining the VGG block over here, right? So that's the first part, right? As we know now, right, in case of a VGG block, we are supposed to use convolution layer with some padding. there is a non-linearity that is coming into picture, plus the out channels as well. Number of the output channels are there. So three things we are using. So according to that, we have done this. Then there is a specific value mentioned over there, right? If you see there, the original VGG network used 5 different convolutional blocks. So the 5 different convolutional blocks are of the specific size. In the diagram, it is mentioned. So according to that, we define. Okay, it's a tuple, right? It contains tuples. You can see 1 comma 64, right? 1 comma 128, etc. Right? So first is a convolution layer, right? So normally you can see that it says 64 output channels. How many inputs, how many outputs we are trying to write over here. All right. So then we define the VGG function, right? So whenever I pass that particular architecture, because each of them, right, each one is different, each convolution layer is different. So according to this particular value, 1 comma 64 enters here, we are generating a VGG for that. Okay, that's what is happening inside this part of the code. Okay, we have a question. Let me answer that first. So yeah, saying that not able to install D2L in your system. Okay, so Sneh, you are trying using the Jupyter, or are you running the Colab which I have shared?
No, sir, I'm using Jupyter, so I'm just saying that it will show some error. I will look.
Yeah. As I mentioned, when I try to do the same thing, right, even I face the same issue. That's why I shifted to Colab. Okay, one suggestion is that if you want to do this on the Jupyter itself, create a new environment. Don't install on the same environment, because of that's what was my mistake. I didn't have enough time to create a new install new environment and then install everything over there, because I need TensorFlow, I need Keras, I need the GPU support, I need everything, right? So all of them installing again was a difficult task for me under the circumstances. So I never did that, right? I directly went to the Colab. Okay, so that's why I shifted to Colab. But yes, what is suggested is create a new environment, and in that, right, whenever you create an environment, just mention what all the things you need. Like you need a TensorFlow, you need Keras, you need everything, whatever you require, write it in the same sentence, so that that will give you the most compatible versions of each one of them, so that there is no issue, no error. Okay, so that's what is suggested if you want to go for the Jupyter. All right. Okay.
Okay, sir.
Yes. Fine. So in this code, we are simply we are passing that convolutional architecture required. 5 are there, because in this particular technique, which originally they invented, they used 5. So we are using the 5. We pass them. We get the VGG architecture. Then directly run the next part of the code, which says that yes, we are printing something. So what is the what are the various layers, and what are the names, what is the size, we can print it. Okay, that's what is happening over here, right? So then yeah, we have defined a ratio for that, right? It is like we are, as we move, we are reducing the structure, that's why. So then we have the same similar code coming up. We are directly training them, and simultaneously we are getting the testing results. And important part is this, right? So as expected, VGG should give better results, right? So we are getting something around training accuracy 93%, and testing is 92. It's, since the data set is same, maybe there are differences among the weights initialized, time taken, etc. So you can see that, right? How many images have been processed in a second, you can see that. Okay, 752 per second. So this is going to change. If you look at a previous case, that is different. It was 1425. That means the previous code ran faster compared to this. Again, you use a GPU, this is the number we are going to get. But if you look at the CPU version, which is getting connected, and if it runs over there, you will definitely see that this is not so fast. It will be slow. Okay, so this is what we have observed. Again, I suggest you to change these values, the batch size, number of epochs, and the learning rate. For a different values, definitely you'll get to different accuracies over here. So, right. So again, as expected, our graph gets plotted in the same way as the training progresses. This is how it gets plotted initially, and you will simultaneously you will get a plot of this as. Okay, so whatever was our expectation, we are able to see that yes, that is happening here. Correct? It's increasing from the accuracy. Initially, you don't have accuracy because you have higher loss. So d minus y is higher, right? That error is more, so you have a bigger loss, and this keeps on reducing as the time progresses. Same thing happens with the accuracy, which is inverse of that. If that is reducing, this will increase. So according to that, right, we can see that we get a plot like this. All right, so fine. Anyway, I don't want to go to the next one because it's a break time. Before that, is there any doubt, or I want to know anybody able to run the Colab on your system connected to GPU or?
So yes, sir, I have selected GPU, so
Okay.
it has selected, but in the last line, it's it's showing same error. This matplotlib backend base error.
Oh,
This cannot import name. This error.
okay. So I was getting the same error. Let me check.
I think.
What was the error? This one.
Yes, yes,
MATLAB.
same error. Yes, yes, yes.
But GPU is connected, is it?
GPU is connected. Yes, runtime. From there, I selected GPU, so it is connected.
Okay, so you don't have any error like I'm getting, right? When I change the runtime or something.
Yes, yes.
You're not getting any error.
Yes, yes. It is selected.
Okay, now it says reconnect. Let's see. No, anyway, I'm not able to do that. Okay, so this is installed, right, on your system?
Yes,
same
sir.
thing like this?
Same
Okay.
thing.
Okay, only here you have some error. In the last part, right? So this maybe you're facing error over here, correct? Okay.
Yes.
It says there is a figure, but figure is not being plotted, right? Okay, let me check. Right now, I'm not able to understand what is this exact error, because everything what we required is there, but it's saying that you cannot import something. Okay, let me try something in the break so that right, if something works out, I'll right. But anyway,
Okay, sir.
so since I ran already earlier, I have an answer with me, at least to see that what's going to happen. If we resolve that error, I'll update you so that I'll update in this particular notebook. It gets saved, so you can load that once again from your system, and you should be able to run that. Okay, I'll see what I can do.
Okay, sir. And if I just run this AlexNet and other, I'll get the same error if I'm not able to see the graphs. Let's run this AlexNet and other one. Okay.
Yes.
Okay,
So,
fine.
all right.
Okay, I'll run.
Yeah.
Okay.
Okay. So, anything else to discuss? Anybody else? Any doubt? Okay. So we'll break for our lunch, and we'll be back by 1:45. All right. Okay. So we'll take a break. Sneh, can you are able to run the code now?
Yes, sir.
Okay, so let's do one thing. Since I could not run that part of the code, can you share your screen so that all can see? Okay, that
Sure.
the running part of that. Okay, so only the plotting part. Right?
Sure, sir. I'll do. One should. So right now, I'm not able to share my screen.
All right, kindly check now. I have given the permission so that everyone can share. I'll stop sharing from my side. Maybe that
Okay,
will
sir.
help.
So is it visible?
Yes. The screen is visible.
So this is epoch equal to 0.9.
Yeah, okay. That one you please run so that we can see the plot is how the plot is going to come. You are connected to the GPU?
Yes, sir, I'm connected to GPU.
Fantastic. Okay, so then it will run a little bit faster compared to the CPU.
It takes 1 minute previous time. I don't know it.
Yeah,
This time
approximately similar, right? So everyone, please see the screen as we are connected to GPU. We'll get the plot. Plot gets updated every time a batch of data goes into the machine. So since the data goes into the machine each time in a different way, there will be a shuffling. Okay, so we cannot expect the same graph which I got earlier the other time when I run. Okay, so there will be variation, right? So that's absolutely fine. So also the accuracy which we got earlier, that might change. Okay, because every time we are training the machine, right, in a different way.
Okay.
The training loss is not actually being plotted. Looks like some issue.
So I've trained this.
Yeah, other one,
I
right?
run this code as well. So maybe.
Okay, let's see. So first, let's see what output we get here. So normally it will plot everything. Okay, maybe
Previously it was.
Yeah. Please go ahead.
Previously it was plotting all three graphs.
Yes. So now that's what is expected when we call this kind of graphs. All the three will be plotted together. Now it looks like there is some issue. Again, the testing accuracy is a constant. Again, that's a hint that right training is something is not correct. So and there is some other issue. Okay. Anyway, that's fine. So anyway, I think everybody has the code, right? So others, how about others? Are you able to run? So let's wait till the 10 epochs and let's see what happens. Okay, so maybe if something happens, something better than this, then we'll be able to find. But anyway, now we are able to see that it's getting plotted as the training progresses. That was my intention. But in this case, right, anyway, there is some other issue. Okay, we'll see that at a later stage. But since everybody has a code, when you run the code, you please make a note that training loss accuracy for training as well as testing get plotted all together. All right. So right. Okay. So yeah, thank you, Sneh, for sharing the screen. All right.
Okay, sir.
Okay. So anybody else who could run the code, because I think the code works. Code is fine. If there is some other issue related to the network or from the connectivity we have with the Colab server, etc., we might face some difficulties in running. Okay. Yeah. So anybody who could run or who wants to, if it is running properly, you can even share the screen. Okay. So kindly suggest if you have, if you are able to run or any inputs you want to give. All right. So we'll proceed further. Right. So after the VGG, we'll move on to the next type of network, which is called as the network in the network. So, so far we have seen the LeNET, AlexNet, as well as the VGG, right? Wherein the design pattern was something like, right? You try to give an image input, try to extract the features of the data which you give, right? And you will be doing that by means of the pooling convolution layer followed by the pooling layer and its various types of representation of that. You may use a convolution followed by convolution, again convolution, and then a pooling layer or something, right? So using the in a network architecture, the researchers tried to implement something where you use a fully connected layer, not at the end, much earlier, right? So that was a new idea which they had. Okay, so to understand this whole process, we'll try to recall two things. Again, they fundamentally call what use what is called as a NIN lock, but in order to understand that lock, right, we'll try to recall something which we already have used or already we know. So the first thing, try to remember. Okay, let me bring a slide. Okay, so the inputs and the outputs of a convolutional network, which we have already used, right, has, right, the various dimensions you can define, right, length, height, width, right, the number of channels, etc. Right. Again, the input and the output of a fully connected layer, right? What do you expect? There it is 2 dimensions. Before that, in the convolutional neural networks, output can be of higher dimension because I'm using many filters over there. Right? So because of that, I get multiple dimensionality, right? But when you go for a 2-dimensional, when you go for a fully connected layer, it will be of a 2-dimension case. Right. Now, what we'll try to do here is that for each of the pixel that is present in an image, right, you will try to use, right, you'll try to use one neuron for that. Right? In a sense, try to connect a fully connected layer at each pixel location. I have an image, right? I use a fully connected layer so that every pixel's value will go to all the neurons present in a fully connected layer. It can be maximum 2D because that's what we already have discussed in the basics, right? So that could be, you can consider that as a 1-into-1 convolutional layer, right? Because for one pixel I'm using one neuron, right? That one neuron will work like a 1-into-1 convolution layer, right? So that's the fundamental idea they have used. So you can see this. So the fundamental block is called as a NIN block, right? So they are using a special right layer which is considered as a 1-into-1 convolution, right? It's of a size single, right? You will use in order to extract something like a feature, you use a single value in a filter, right? That because of certain research, they could come to know that okay, even you can apply a 1-to-1 convolution possible, and this is going to give you certain type of result, right? So that NIN block, right? You see, first one is a convolution followed by two 1-to-1. So that is repeated usually. You see, this is a NIN block. This is another NIN block, another NIN block, and so on. Between those, you can use a pooling, right? That's what they show, right? So there is a pooling that is happening. Pooling size, they have fixed it to 3x3, right? With a stride of 2. So it's the same. You can see that max pool 3x3 stride 2. That is what they have used. All right. At the end, you are using a global average pooling. All right. So this kind of structure has been named as a network in the network, NIM structure. So the to be precise, the following are the convolutional layers window types. What are they? 11x11. You have a 5x5, okay, and 3x3. Right. So maybe they use this from the AlexNet, same as AlexNet, right? Then each of the NIN block followed by a pooling, right? Between two NIN blocks, you have a pooling that is a maximum pooling, right? And right, NIN avoids the fully connected layer at the end. Later on, at the end, you see that we had that 3 or 2 or at least one layer of fully connection, right, between the convolution and the final output layer. Maybe at least one layer you will have that is completely connected. Every neuron is connected to it. But now you see it is being avoided. That's the fundamental difference that we can observe, right? So because of avoiding say 2 or 3 layers of say 200, 300 or 500 neurons, each neuron connected to every other neuron, you are trying to reduce the number of parameters, in the sense the weights. Total weights required to train have been reduced drastically. So that is what is the it's a fundamental structure and fundamental idea behind the NIN structure. Okay, so please go to the code what you have and try to run the NIN code. So from the basics, we already know that the requirement is that you need to define what is it block, right? How the NIN block works, you have to first implement that. So you see here in this code, NIN block has been defined, and according to that, it's a sequential layer, one after the other. We are connecting layers. So what are the layers? There is a convolution 2D, normal convolution 2D. Then convolution 2D, this will be of size 1. Okay, you can see the kernel size is fixed to 1 for both of them, because that's what is the fundamental NIN block looks like when we saw the architecture, right? Then, right, you can use these NIN blocks many times to create your final structure. That's what is in the next part of the code. Again, that is sequential. See, we are calling the NIN blocks many times, right? Between the blocks, you are using the max pooling. All right, so that is repeated as many times as you want. And finally, I'm trying to flatten this, okay, so that you can get the outputs, right? And we will print, right? We are able to print the layers, various layers possible, that is over here, okay? And you can see that once we call the training as well as the testing part, right, we get a graph something similar to this, again simultaneously plotted when the code is run, okay? And we could obtain 86.7% of accuracy in the training part, and the testing accuracy was 87.7, right? So this may vary. So those who have who could run this, right? So please put a message in the chat box how much accuracy you are getting. Okay. Once you get the accuracy, please put a message over there so that we will be able to understand the difference in the sense, right? Though the code is same, right? Since the way of providing the input varies from machine to machine, right? We can expect that a different value might come over there. All right. If anybody has obtained the accuracy, please put your accuracy over there. Only two values. We'll understand that. First one will be training. Second one will be the test.
So actually on my Jupyter notebook, I could run this code.
Okay.
Yeah. And for the first LeNET algorithm, I got the graph with a train accuracy of 81.9 and test accuracy of the same. And I could see all the three graphs. For AlexNet, it is running right now.
Okay. Okay. All right. So you have a GPU in your system, or how much time it took for the first one? Do you have any idea how much time it took?
It's like, it's example for seconds. Where I can see that time?
No. You as of now, you don't have a facility to visualize the time it has taken. Okay, so maybe you can keep a count of by just as of now, we don't have that facility.
Okay.
Okay, so just approximately, I just asked. Okay, if you have noticed, you tell me. Otherwise, it's fine. Okay.
I do have my machine, the GPU. One maybe that 4 GB.
Okay. Then you are running on the much faster side. Okay, so since it is running on a GPU, so you whatever answer you're getting is is actually much quicker compared to the CPU. Okay, right. So note the in the sense, just note how much time it is taking. All right.
Yeah.
So it is showing that it's running on the GPU, right? Like some CUD or CUDA, it's running on CUDA 0 or something like that. You are seeing that near the
yes CUDA 0.
CUDA.
Yeah, I could saw that.
Yes. So that means it's running on the GPU itself. Okay. So if it is CPU, it will take a lot of time more compared to this, but it is expected to run within 2 to 3 minutes for a simpler one like the LeNET, and the AlexNet will take some time. So as you proceed further, you will see that it takes more and more time because we have more and more layers coming into the picture.
Yeah.
So time complexity is actually going to increase as we move ahead. All right.
Sure.
That's good.
Yeah.
That's good. Okay. So everybody, please note when you run how the plot is getting updated. So ideal scenario will be something very similar irrespective of which algorithm you are trying to run. Initially, you have a loss higher value. It keeps on reducing, and as that loss function reduces, you will see that accuracy keeps on increasing. This is what everybody should know. Okay. Any other doubt? Anything? Any input from others? Are you all able to run either on your Jupyter or on the Colab? Anything you want to discuss? Otherwise, we'll proceed to the next one.
Actually, on a Colab, I was getting a same error that you got.
Okay.
That
okay.
The extra variable which is not defined for MATLAB.
Okay. Fine, but actually the code is fine. Some error from the Colab side. That's what I could guess. Okay, because you see that others could run, right? So no issue with the code in my knowledge. And you could install that D2L in your system, I guess, right? So
yes.
Okay. So
whatever is required for that also I have installed because it requires the other. First, you required that PathLab, then you required some other even I had to install the torch.
Yeah. Okay. Correct.
So all that, like, okay,
Yes.
once that I could successfully done it, then it worked
Then
properly.
it works. Yes. Perfect. Right. So compatibility issue will be there almost every time whenever we try to use a new module which has not been used so far. But yes, so if you are able to tackle that and you could make the compatibility, you could resolve the compatibility issues with all the other tools, yes, definitely it will come. All right. That's right. Okay. So we'll move to the next one, which is called as a GoogleNet. Right, so this was 2014 when the first implementation of GoogleNet came into picture. So they again, it is a fundamental block based, right? You are using the other blocks like convolutional polling or the activation function layer, etc. In addition to that, you will use their fundamental block called as a inception block. Now, this particular network is completely different compared to all the other networks we consider so far, because previously every network you consider, it's actually a single stack. Now you see here the inception block actually gets deviated. There are parallel calculations happening. So from the input, which is here, you can see, right? So the input, you have actually 4 branches going on. So whatever is the input, it will go through 4 different paths, right? So parallelism is brought into picture for the first time, and they could show that yes, you can bring the parallelism into picture and concurrently you can make the calculations, right? Simultaneous calculations will happen along each of the path, and at the end you will concatenate the results, right? You may have to do a padding or something, because what we can expect is you have different output, right? Sizes of the outputs from each of the layer will be definitely different, right? So because of that, you have not only the depth, right? Because the deep learning expects depth, more layers. You have a breadth coming into picture. You divide them into multiple parts, right? So number of parts you define, right, will definitely give you a lot of breadth as well. So that's what is a fundamental block of a GoogleNet, and you are going to call it as the inception block. Right. So fundamentally, this inception block has a specific set of convolution layers, and the size of those layers are 1 into 1, 3 into 3, 5 into 5. Okay. So again, each path tries to extract various types of features by using various filters, but those filters are going to operate on the same input, right? Previously I had a network, right, convolution layer, it gets some output that itself is given to the next layer, which tries to take one set of what you call features, right? Once I have a feature, I used to give it to the next layer, but now you see same input, I use multiple paths wherein I'm able to take different I'm able to capture different sizes of what you call feature maps. So that's a new thing, right? Because of that, okay, people consider this as something very new, and this got a lot of recognition as well, right? So when we come to the actual model, right? So this is how the model looks like. So fundamental feature is that there are total 9 blocks that were used in the initial version. Okay, now also you get this is again what I'm showing here is the initial version. Okay? So nowadays you can you get the updated GoogleNet model as well. You search that has been modified. Okay, so I saw the recently one network, again it's a part of the Google network. Initially you calculate sum of first few are one after the other, they have been stacked. Okay, after that there is the output will be split into 2 parts, and you have these inception layers are being carried out so many times, like totally they have 141 or something, approximately 140, I guess. Totally 140 layers have been created in that particular version of the GoogleNet. So it's not like just like you have a small portion where you have 4 branches. It is not like that. They have initially some 5-6 layers are there. After the 6th layer or 7th layer, it will split into 2 parts. You follow that like maybe 50-60 layers after that. So once the 50-60 layers are over, you club them together and you further proceed. That's what I observe. Okay, so such versions also will definitely exist now, because now we have much advanced calculations are possible. Again, for the same reason, we have GPUs, we have various filters available, right? We have done a lot of more research than 2014, right? So this is the fundamental block. All right. So anyway, I'll show you the complete diagram. So totally, this is the initial architecture that has been that was defined, right? So in 2014. So let's move to the coding part. So everybody move to the code. All right. So we define the inception as a module. Okay. So we are using the class to define that. Anyway, that's an optional case. Whichever programming technique we prefer, we can use. All right. So you can see that, right? Various types of layers have been defined according to the that particular block which you had seen. All right. So every layer is parallel to each other, because you can see that the input comes same. So in channel, etc. Wherever you see the in channel, it means that is again taking the input from the original input which is present over like that. Okay, and we will whatever is available, you will pass it to the next layer by using the forward function. Right. So then for every layer, right, we are going to define several layers one after the other, because it actually had 9 different layers. So we are trying to define them separately in different parts of the code which you see here. Okay, so each one is a representation of the same block set which you had seen. So whatever specifications were mentioned over there, right, has been specified here. Okay, so many layers were there, and then try to plot, right? Try to visualize by calling the same for loop, right? Whatever layers are there in the network, try to visualize that. Okay, so that shows you the sequential arrangement of the layers. Okay, so once that is done, then we go ahead and mention what is your learning rate, what's the number of epochs you expect, and batch size, right? So again, first you run the code by yourself with these values, and note the accuracy and right, and also the loss. But later on, I suggest you to change these values and right, run it again. Okay, so if you are running on the GPU, it will not take much time, maybe 4 to 5 minutes per run, I guess. Okay, but the CPU will take a considerably large amount of time. Okay, so anybody who ran this part of the code, do you have the output with you? Anything, any comment you want to make on this? Yeah, please go ahead. I'll wait for maybe 1 or 2 minutes.
So I have one question.
Yes.
So
please.
here for CNN, we use the D2L library and Torch, PyTorch.
Yes.
Yeah. But we can also use Keras for this.
Yes, definitely. You can go ahead, use the Keras. You can implement the same thing using the other libraries. Many libraries do this. There is a transformers. There is many things like this. Yes.
So
definitely.
what is recommended? Basically, what are the which one is the base that or a guide? Which one we should be focusing more? Keras plus Torch, or is there any suggestion or a guideline, so that we can go in depth in those libraries?
Okay, like that. Okay, so I would suggest you to look at the PyTorch is again widely used. So, but depends on what basis you want to use it, right? Normally, PyTorch people prefer in the NLP side as well as the image side. Okay, so that's why here image we using that. Okay, general machine learning algorithms, general deep learning, right? It is expected to know the TensorFlow as well as Keras. Okay, so anyway, Keras will come about TensorFlow. So I think I mentioned once, if your intention is just to run the code without knowing what is on the background, Keras is preferred. You want to go from scratch, right, etc. You want to do a research like a PhD or something like that, then the TensorFlow, starting from scratch of the TensorFlow is preferred. Okay, so these are the widely used things. So these three are, according to me, should be sufficient if you want to go in depth. But we cannot say only one, this is the best one, because of the constraints. Like, okay, so what hardware, some of the functions written in the TensorFlow might work faster on my system than the Torch, or vice versa. Some other functions might work faster here and there. So these are the three things widely used. Okay, so TensorFlow, Keras, Torch are most preferred, right? Again, if you go to industry side, some use only the Torch for their development. So in that case, you need to know the Torch in detail. Otherwise, right, some use only the TensorFlow because Google has a good support side, etc. Right? So these three are recommended.
Okay, thank you.
Yes, sure. Okay. Yeah, Jyoti gets loss for networking network 0.34, 87% training, 86% testing. Yes. All right. That's good. Yes, for networking network. Right. Okay. So anybody else who could run the code for the, this is what we are running, right? GoogleNet. Anybody got output for GoogleNet? Okay, okay. So we'll wait for maybe 1 or 2 minutes. Anything you want to discuss, any general topic related to the previous question or something, so that we'll make sure that everybody is together. It will take some time, yes, Susne, because GoogleNet is considered to be, even this is the oldest version, it takes some time. Okay. So you can see here in my case, the accuracy was training was close to 90 and the testing was around 86. Okay, so also we can see something, this is not expected on every machine, so you can see, you can note that something happened here. So loss increased and the accuracy is reduced all of a sudden, but anyway, since this was at the middle, right, no issues, right? Later on it proceeds further because some of the new data set entered into the machine which it didn't know, it has not learned. So there is an error all of a sudden. Okay, so error was high, so weight updated so far, you can say that is of no use, right? Because something new came up, it didn't know how to classify, so there was an error, but all of a sudden it learned, and you can see that, right, by the time you reach the epoch number 8, right, it could come to the same level, right? So it happens.
Sir, will we read CV library for the like vehicle counting kind of project?
Yeah, for which library?
CV, sir, computer vision. There is some CV library.
Yes. No, we will not touch that in this module, but maybe for a project at a later stage, we might use it. Okay, if it is, when we do that, if it is required, we'll bring that. Okay, and we'll discuss the basics, and then we'll move on. Okay.
Okay, sir.
Sure. So next topic will be, I think, the NLP, I guess, natural language processing. So for that also we can use any libraries. We'll see what we can, what's the best we can do. So Torch has a lot of support for that. processing the languages, there are many functions which support, right? Directly we can call it and we can do what we want. Same thing goes with the TensorFlow as well, right? So we don't prefer Keras for that. But anyway, Keras will also support, but we'll try to stick to either PyTorch or the TensorFlow. We'll try to write we'll take a problem, we'll try to write that using, we'll see how it works. Okay, so anybody who get the result for the GoogleNet, if it's still running, no problem. We'll proceed further. When you get an answer, you please put it over the chat so that we'll come back to you. We'll discuss your results and then we'll proceed. Okay, so let it run. Once you have a result, please put it in the chat. All right, so then let's move to the next method or next architecture, which brings a new technique into picture. Okay, so this is called as a ResNet. It's called as a residual network. So far, the idea is this: like I have an input image, consider that as a vector x. So that vector x goes into a convolutional layer or any other layer. So consider what operation you are performing by the convolutional layer on the input. Right? Consider that as a f of x. X comes, perform f of x, get an output. All right, so that was the fundamental idea. You repeat this again and again many times. So I have a f of x, next I get a g of my y, because f of x is what I'm going to call as y. Next layer will perform g of y, gets an output, like that. You see it processed, right? It's going to be processed in the same way, right? Increasing the, what you call, increasing the layers increases the complexity, right? But in 2015, right, they tried to implement, let me show you the block so that we understand what exactly they are trying to do. Anyway, there is a block which is called as a residual block. Almost everything that is newly implemented is block based, because you can simply write a function for the block, keep calling the block again and again, instead of calling the something like the fundamental block convolution rail again and again, keep it ready. This was the technology used even in the circuits when we go for VLSI design, etc. Right? You will observe the same thing. You don't design everything starting from the transistor level. You keep something ready. Amplifier, okay, this is the amplifier. You want a filter, okay, this is the filters. Everything is ready. Simply bring the block, put it over there in the circuit, and keep good. So it's like that. We don't go to the very most basic level like convolution layer or the pooling layer, etc. Make a group of that, like build a bigger circuit out of it and use that as and when you want. So that's the idea. But let's look at their what they're trying to do. Why the word residual comes into picture. So by using a set of layers, right, calling it as a block, you are not calculating f of x. Okay, here their intention is that you have a x input, calculate the fx minus x. Okay, calculate fx minus x. That is what they are calling it as a residue. Right. So this was their idea. Fundamental idea is that then you also take the x over there, right? If this, they're saying that you need to minimize this. They have a mathematical calculation to prove this. Anyway, I didn't get that much time to go in much detail to understand that. The whole calculation is more than 2-3 pages, right? Pretty complicated notations also do exist over there. But what we could understand is that they call the fx minus x as the residue. For when you give x, it passes through a set of functions, you get f of x normally, but they build that function to calculate f of fx minus x. Call it as the residue. Okay, so residue has been used, then that is passed, added with the original x. X comes from a different path, you can see here, gets added, and you pass it through the activation function. So this whole thing is the fundamental block of the ResNet. You call it as a residual network. Okay, so we have two options here, right? Again, they divide their ResNet fundamental block. They say that you can implement two things over here. One is that, right, you can take the input directly, right, and pass through your ResNet block and keep the X coming in as it is, and then you pass it through the activation function. That's the first option. And the second option is that when you take X, right, directly, you pass it through a convolution. Two things are. Okay, so two options. We can use anything you want. Okay, so that is the fundamental block of the ResNet. Okay, so before going to the whole model, I'll read the messages on the chat. Okay, so Snake says training accuracy 0.90, loss 0.24, and testing accuracy is 88%. All right. So Jyoti gets 90.8 and 0.877. Right. So yes. Right. So you can see that there will be variation. Right. Slight variations will be there, but approximately close answers. Okay, so those who ran that, move to the next one. By the time we finish this and we come to the code, maybe you will get an answer. Okay, so please proceed further to the next this thing. Try to run the ResNet part of the code. Okay, so ResNet, the fundamental block, yes, we understood, right? Now we'll go to the model, right? So ResNet model has various versions present in it. So initially when they used it, they actually have various types of various arrangements of these fundamental blocks, because initially you can see that there are two blocks defined as it is. You can make various combinations of these blocks to get different what you call combination, different setup, right? So because of that, right, you can see some of the names I tried to mention here. In one of the architecture, right, there are 4 different convolution layers at each of them. So together it's a 7x7 convolution layer. So totally when you calculate, you have 18 layers over. Okay, pretty much complicated one compared to all our previous the previous architectures. So since there are 18, they named it as ResNet 18. Okay, this, as I mentioned earlier, you can actually make various combinations as well, right? So there is one particular ResNet model which goes up to 152 layers. Like I just mentioned in one of the cases where I saw the GoogleNet with 140, right? That's not the ultimate one. You can identify the different networks with different orientations of the blocks to get much deeper network. Now you see 150 layers. We started from initially 1-2 layers of neural network, right? Neural network hidden layer. Now you see it has reached 152. Okay, so again, this is just a number we are showing here. We are discussing. You can see much deeper networks as well. Okay, so because of the 152 layers we have, right? So this is called as ResNet 152. Okay, so now let me show you the ResNet. This is a ResNet 18 diagram. Okay, so right, so we can see, right, initially the data comes, 7x7 convolution happens, then a batch normalization, 3x3 max pool. Okay, and so batch normalization, I think we have never discussed in detail. So it's like you made a batch, right? Batch of data. You try to normalize by using some equation. Normalize the parameters you train. Weight can be, maybe it's most of the time it's weight only. Okay, you use a normalization, right, to do that. So 3x3 maximum pool. Then you can see the fundamental ResNet blocks one after the other. So somewhere you are not using the convolution. Here you can see you are using the convolution, again not using the convolution, and so on. This goes, right. So we can modify as per our requirement, but we are able to understand that, okay, these many layers required to solve this kind of particular problem. Now you see, this is what is the state of art saying, right? Again, each of the state of art methods or neural networks we discuss is giving you something close to 90 without making any modification. Simply I'm typing some learning rate, some epochs, and some other values, right? See, simply giving that value is also giving you close to 90. That's what I mentioned when a question came yesterday, right? What do you expect normally? Close to 90 is expected. More than 95 you can definitely get if you modify those values. All right. So yes, so that's the ResNet. Now let's move on to the code part. Okay, so here also we define a class called the residual. Inside that we build, right, the network, right? So you can see that convolution 2D, right? Then if at all use 1 cross 1, right? We are defining, if at all we mention that we need to use 1 cross 1, we have an option. Do you want to use it or not? If you say no, false, this part of the code will not be implemented. It will be simply connected. Okay, so that's what. So you see, if it is there, do this. If it is not there, simply connect. Okay, so that part will not come into picture, simply connect. So then how the forward connections are made, that's what is there. Then you can see, this is just a test, okay? So don't worry about this part. We were simply testing whether it's going to generate the particular array or particular size or not. That's not needed. So then we define, right, the 1 by 1 layers we defined over there. So that's a P1, right? Then each of the ResNet block we define here. So according to the requirement, right, we define the blocks. Again, by referring to the original block which they have mentioned, we'll be writing this. So then call it, right? So B2, B3, B4, etc. you can call, because everything is a ResNet block, right? Then convert them into a sequential, right? Just mention that, okay, this connect after this, after this, after this, etc. You mention over there, right? So immediately after that, we will try to visualize. Okay, so once we call the print, it prints up the various layers, right? That has been defined. So everything is as per the original block mentioned. And you see here, we will try to perform a learning as well as the evaluation of the performance. Okay, so we can see this. It says that, okay, again, randomly I gave 0.05. I think previously I mentioned 0.01 or 0.1 something. So it's randomly given. Try to keep the epochs constant every case. But this I try to change. Sometimes 128, sometimes 256, right? Okay, so when we are running this, I think, okay, so training accuracy was 99.5, testing accuracy is 91.3. So well within the range, right? 90 to 95 normally we expect. This comes inside that. Okay, so tell me how it's going on from your side. Are you able to run this part of the code? It should be running now, by now, I guess. Still running, I guess. Okay, so once you get the output, please let me know by mentioning that in the chat. Okay, meanwhile, if you have anything to discuss, please ask the question. We'll take 1 or 2 minutes here, and then we'll move on to the next one. Okay, so Sneh is getting loss of 0.013. It's very minimal, so we are expecting a good result over there. So it is supported by training accuracy 99.7 and testing accuracy of 91.6. Okay, pretty much closer answer. Okay, so yeah, Jyoti is getting 99.9, 92.4. Yes, perfect. All right, so hope others also working simultaneously with us, and let's move to the next one. So this is called as a densely connected network, commonly known as DenseNet. A lot of research is being done right now on the DenseNet. All right, just because of the feature of the DenseNet. So they are trying to consider. You can consider this to be an advanced version of the ResNet. So ResNet brought up the concept that input can be taken and given as, right, from the input you can take a connection out and give it as input at any point you want. Okay, So that itself has been used in the dense network, and you will try to connect your input to every layer that is present. Okay, so input is taken and given as a connection as an input to each and every layer that you have. So this makes the final layer, whatever you have, right, that will be pretty complicated because that gets input from every previous layer, not just input. Okay, so input is connected to every layer, so every layer's output is connected to the layer that is after. So right, so there are two types of the dense, right? Anyway, I'll show you only one of them in the diagram. So there is some mathematics associated with that, so when you read it, maybe it will help you out, but as of now, don't worry about this. So previously the ResNet was doing something like this, you can assume, right? So x plus a non-linear function g of x was being implemented. Now what is happening, right? You don't do the addition here. This was ResNet. DenseNet will perform a function over. That's all. So it's something like, if you want to write a mathematical notation simply like this. So right, we are trying to get the, from every layer we are trying to get an output such as this. Initially you start with the x, then you have f1 of x, f2 of x, and x1, because you see x is given as input to that, right? f2, the second layer, takes input from the previous layer as well as the x. So you see the next layer takes x as well as f1 as well as f2. So everything goes over there. You see here. So this is the diagram, one type of the dense net which we are talking about. So just see, x goes input to the last one, x goes input to the previous one, x goes to the input to this. At the same time, right, x goes an input to this, so this is calculated. Now you see the connection for the second one, it takes this as well as the previous one, so two inputs to the second. Look at the third block. Third block takes how many inputs? Three inputs, one from here, one from here, and one from here. So 10th layer has normal inputs coming from the previous layer plus all the inputs from all the previous layers. Like the fourth one will have four inputs, one normally coming from the previous layer, one from its previous layer, one from previous, one from its previous, before that. So that makes the word dense comes into picture just because the final layer takes so many inputs. Normally whatever comes from this, right, it depends upon, you see, how many neurons are there. If this has say 100 neurons and this has say 200 neurons, 200 to 100 connection will be there. That much connections are going to exist by default. Now you see, it also depends upon how many neurons are here, right? So that will also get connected to this. How many neurons were there previous to this? It may be 500. All the 500 will get connected to this. Before that, input may be of size 25. All the 25 will get connected to this. So this layer looks pretty much complicated, right? It's very dense. Now actually dense is used here. This is the proper dense which we are calling it by the, it's properly termed. Okay, so previously, initially somebody called a dense, right? That was for the fully connected layer itself. So now, anyway, dense means this dense. Okay, so that is the fundamental architectural difference. So for the dense layer, and let's go to the coding part of that. Right, we'll try to define various blocks. Every time I'm going to call a convolutional block, so we'll call the convolutional block here, then define the dense. As you can see here, we define a dense, and we need to forward whatever is given. We can forward that to the next one. So again, so this part you don't worry, it's just a testing part. So whether we get in what size we want to we were checking over here. So we define a transition block, input channels, and the number of channels totally, because for every layer, right, I had get the inputs and the previous layers coming into picture, right? After that we will call, because these are the fundamental blocks which we keep calling again and again. So that were defined over there. Now you define. Okay, so sequentially you can define, right? So that's the first layer, right? Like that you can do the next part where you actually calculate the number of input layers required for each and every block that is present, one of them, right? Then we go to the sequential. This is the network, right? So once you do the network, then yeah, so network is defined over there. At the end, we do like this. Okay, so we call the training this thing. So as soon as the training happens, right, you will get, I think we got 94.582. All right, so this will definitely vary. Yeah, I think we have answer from Jyoti, 94.6 for the training and 91 point, okay, 91.0 for the testing app. Right, so others, when you get an answer, please post it over here. Okay, so we got answer from Sneh as well, 94.9 and 89.7. Right, so by this we can understand that as and when we vary the data in the format in which data goes into the machine, it's random. All right, so because we maybe all of us are running on our own systems, right? Everything goes in random, so the way it enters into the system also matters. That's what we can conclude from here. So same algorithm, everything is same, right? We are generating different answers here, but that's well within some range. Okay, so that's why we can say that all are the acceptable answers. So in addition to this, I expect you to work more on this by changing the parameters, just see what happens. Okay, yes, so any doubt with the anything that we discussed so far?
So
Yes.
what is the objective of using these all CNN layers? Like what at the input side, we are giving this MNIST data set. What is a target? What information or we want to extract from these data sets?
The classification. So actually internally what happens is it gets divided, right? Some part of your data, this data set has I think 60,000 right data.
Yes, 60,000 data.
60,000. It gets divided 40,000 and 20,000 according to my knowledge. 40,000 used for training, remaining 20,000 maybe. Okay, approximately close to that, maybe number differs. Right? Okay, so it gets trained using the training data, and it also simultaneously gets tested with the testing data, which is not known to the machine. Okay, so in this code, what happens is it will train, you will get a training accuracy. There will be a validation. Okay, so during the training, it's like I'm teaching you something. Immediately, I'm asking you a question, just to check that whether you understood or not. Like that, it validates. That's what is a plot that is being shown here as a training accuracy. Whatever has been learned, is it able to recall immediately after training? So that's what gives you the training accuracy. After that, it automatically gives the testing data, which is not known to the machine. Machine never learned that during the training phase. Testing phase gives you, right, the idea that, okay, if something new comes, how the machine performs, how it is able to make a classification, right, from the from whatever it has already learned, provided the testing data set is not known to the machine. So that is the objective that is actually being performed here in every code. So we are trying to look at various stages, how the deep neural network evolved, starting from oldest till the newest one. So the DenseNet, whatever you are seeing here, right? This can be considered as the most recent one. Okay, so we started from very old, we came till here. So the objective behind using this in a class is just to make sure that you know these terminologies, and at least you should know that, okay, this is how to code them if required. All right, so these are the state of art, right, as I already mentioned. So you may have to use something, because you may go for a ECG classification algorithm, maybe you want to implement that, right? So maybe you want to try all of them because they are standards, right? So maybe you will do some modification at a later stage for your requirement, but definitely, right, the whole architecture and how the blocks are arranged, etc., and how to code that, this much at least if you know, right, you can definitely improvise on. That's the fundamental idea behind this. And in this particular example, we took the same problem just to compare, right, with all the others. Okay, I hope that is clear.
Yes, it's the same as pattern matching, like
Yes,
60,000
yes,
pattern in the
yes,
input, and we
yes.
are giving the pattern and checking is it present or not.
Yes, yes. So 10
Okay.
classes of data we have here. So we are expecting the machine to classify the incoming data to one of those 10 classes. If it is wrongly classified, it will consider that as an error. If it is correctly classified, it will take that as a correct thing and increases the accuracy.
Yes, sir. Okay.
Okay. Yes.
So one question.
Yes, sure. Please.
Previously, we said that, okay, we have to decide on a filter size and a filter. So here I don't see anywhere that filter is like, okay, filter is like, okay, set to some particular metrics or value.
Yes.
So I'm little confused on that front.
Okay, I'll come to that. So on all these techniques, what they have implemented is that you initialize the filter with your specified size. Okay, maybe 2 cross 2, 3 cross 3, 5 cross 5, etc. Right. So these algorithms, they will actually update even the filters internally. Okay. So initially, yes, as you mentioned, right, we discussed that filters we fix it. Okay, so filter size is fixed. So I want to detect this pattern. I will say that, okay, it's 101, 010, 101, something like that. I fix it, right? But as the technology evolved, right, you don't have to update only the final the final fully connected layers. Not only that, you will also update, right, the weights of the filter values itself. That itself is a weight, right? So every filter value you can also update. So initialize something, then it gets updated. Okay, so that's the answer to question. We don't have to specify any weights, any values over there. So simply mention a size, it will randomly assign, and then it gets updated.
Okay.
Okay. Yes. Yeah. Anything else? Any other doubt? Let me know if you have any other doubt, anything to discuss. So these are the very standard ones which I consider them to be important. Okay, one of them we might use. Either you may get a pre-trained network such as GoogleNet, etc. The GoogleNet, the standard one, if you try to download from internet, it already has been trained and it is capable of identifying 1,000 objects. That's why there were so many layers, 140 plus. Okay, so you give an image of a plane, simply test, directly test, don't train, no training and all. Okay, so it's already trained. Simply give a image input of out of the 1,000 categories randomly. You can choose a book, you can choose a car, you can choose something like. Give us an input, it will tell that, okay, this is a car. It's already trained. Okay, so many layers are there. It's already trained. Right? So some standard pre-trained models are available. Right, so you can explore, right, on that. You can download, but anyway, so the architectural differences among those standard networks and how the networks evolve, right, starting from 10 years ago to now, you can see the difference every time, right? They are adding something new, some new connection, right? There is no parallel paths, that was also brought into picture. There is no something like a feed forward, right? I have something, take an input to every layer in the next one. That actually helps in some way, right? So to understand that, people have done a lot of research. Okay, at the end, right, these are the various network architectures which we consider as standard, and I want you to know the architecture, how it looks like, what are the possible layers and what are the differences, only that. Okay, because coding can be done in any way, right? You get a lot of references even in the internet, how to write a code for a particular thing. That's fine, that we can use, right? So that nobody can expect you to know how to write it from scratch directly. All right, so at least if you are able to remember, okay, this is the block, this is how it looks like, this is a particular block used in this kind of network. If you are able to remember that, that is more than sufficient. Okay, so I hope this session is useful to you, and we'll be continuing with this in, mostly that will be the last class of the computer vision, where we'll solve a object detection programming thing as well. Plus, we'll look at some of the basics required for computer vision, specifically images. All right. So with that, we'll conclude today's session. All right. So we'll meet in the next class. All right. Thank you for your patience.
Thank you.